Good morning, people. Just about ready to get rolling here. There's something important that we need to talk about today because there was an oversight on my behalf in our last little bit of planning, unfortunately. The calendar committee here at Santa Fe is an interesting group of people. I don't know them personally, and I don't want to disparage any of them, but sometimes you gotta wonder just what the fuck they're thinking. Because it turns out that although UF is not taking off their own homecoming this year, Santa Fe is. And you might ask, why does that matter? Well, remember how I said we're going to have our first test on next Friday, which would be the 2nd of October. It turns out that next Friday, the 2nd of October, is UF's homecoming. And although UF is not closing for it, Santa Fe is. So, you know, God help us. We're going to have to figure something out. That's all. Now, right, yeah. Well, so I agree with those two sentiments. What in the hell, and can we just have class anyway? We're in a bit of a weird situation. Because this is a hybrid VSync class rather than a fully online class, I'm obligated to follow the schedule of the college. I'm not allowed to have class on a day when the college is closed. But I mean, I won't tell if you don't tell. I don't know. I'm not sure exactly how to put this. So what I wanted to do is get a feel for how you guys feel, what you guys want to do. So basically, we've got two options. We can ignore the fact that the college is closed next Friday, and that would mean we would have our test on that day. We weren't going to have a lecture that day. We were just going to have our test that day. That was the plan. Or we could postpone the test. If we postpone the test, that means that there's going to be a little bit more of a gap between when we finish learning the exam one material and when we get tested on exam one, right? So we're going to finish learning the exam one material this Friday, next class meeting. And if we waited until, I don't know, I guess it would have to be Monday the 5th, or the 6th, Monday the 6th, then that would mean you'd have, you know, this larger gap, which would mean more study time, but it also means kind of more time to forget. So we've got these two options. So for exam one, we have the following options. We can ignore the fact that the college is closed. We can have the test on 10/2 anyway, as long as nobody here is bothered by that, right? If you have plans, or if for some reason that's not going to work for you because of the college closure, I have to honor that. So I certainly don't want to cause anybody trouble. The other option is to push exam one to Monday. And let me double check the date there. I think it should be the 5th or the 6th, but I can't count, so, you know, the 5th. All right. Okay, I should have covered anyhow. I'd rather take the test. All right, yeah, that's kind of my feeling too. But let's see. So I'm gonna do this. So some things to consider before I let you vote on this. If anybody was planning to take the test on campus, if you wanted to use Santa Fe's Wi-Fi because your Wi-Fi is unreliable, if you were planning to use a computer in the library because you don't have a webcam, if you're going to be working with the DRC or anything like that, be mindful that if we have the test on Friday 10/2, if we do not postpone the test, you can't do any of that because the college will be closed. Okay, so postpone the test, sorry, to 10. All right, so I'm going to go ahead and launch this poll. But please be mindful of what I just said. If you were going to work with the DRC and you wanted to work with them in person rather than having to take care of accommodations online, or if you were going to use a computer in the library to take the test, or if you were going to use their Wi-Fi to take the test, if you were planning to do anything on campus for the test, you won't be able to do that if we keep the test on 10/2. Okay, so I'm going to launch the poll. Everybody should have an option to vote. I will give you guys some time, and I would like to get a vote from everybody in here, which means I want to see 19 responses. So please, everybody just go ahead and vote. Yeah, I mean, if we postpone, that means extra study time. I'm happy to do either one. Oh no, we got a tie so far. All right, I'm still waiting for votes from 5 people. Got 14 votes in now, 19 people here, so I still need 5 people to vote. I'll turn off my share here so everybody can see it. I know it's a lot of pressure. We got 19 people. That's an odd number. I got 2 more people. Oh no, 3 more people that need to vote. So help me out here, guys. Okay, so I see a few people just came in. Right now, I need everybody to please vote on this poll. The college is closed on the 2nd, which is the day that we were going to have our test. So if you're planning to use any of the college resources, like take the test in the library or work with the DRC physically on campus that day, please vote to postpone. Otherwise, just let me know what you're feeling. I'm going to close the poll at 3 minutes, so we got another 40 seconds to decide. I still need votes from 2 people. Oh, sorry, I guess I still need votes from 1 person. I can't vote, yeah. I suppose 1 person couldn't sway it at this point. All right, so the test is going to be pushed to Monday. All right. That's what we're going to do. So I know this is a little bit weird and it throws some things into, you know, makes things a little bit more chaotic, and I apologize for that. I have no idea why Santa Fe is closing for UF's homecoming. I don't know why they ever do that, but especially since UF isn't doing that, I'm just baffled by the calendar committee's decision, but it is what it is. So you'll have a little bit of extra time to study. It means we're going to have to push a little bit harder and move a little bit faster after exam 1. And it also means that next week, there will be a little bit less review and a little bit more covering new material because there's only so much time in the term and we have to keep rolling. So while this does mean you'll have more time to study, it also puts the onus a little bit more on you to prepare. So please make sure you're using the time between now and the test wisely. Make sure you finish all of the homeworks. This Friday, remember, I will be dropping the study guide. So instead of having a week to work on the study guide, you'll have a week and 3 days. That's nice. Make sure you use that time well, okay? Don't put off studying, don't put off doing the study guide. I want to pick up today where we left off last time. We practiced with some trig sub. I've pretty much shown you guys all the trig subby goodness, but I know it's something that takes quite a bit of practice to really get the hang of. So today we're going to practice a little bit more trig sub, and then we are going to learn about partial fraction decomposition, which is very cool stuff. So today, more trig sub. And then an intro to section 7.4, which is on partial fractions. So for those of you who have taken a look at the homework so far, I would be happy to play around with whatever trig sub problems y'all wanted. Are there any particular trig sub problems from the homework that you guys would like to take a look at? You can go ahead and type them into the chat. Zach would like to see number 4. I think I could do probably 2 more. So I'll let you guys choose. Just type the problem numbers into the chat that you'd like to look at. Begin with number 4. Okay. Yeah, okay, let's get started with number 4. That's the integral from 2 to 4 of 1 over x squared minus 1 to the 3/2 power. And I'm going to do this on a fresh page because I think it's going to take a little bit of space. Okay. So here's the game. At a glance, it might not look especially trig subby because you don't see a square root. But remember, like the arctan integral that we did, our very, very first example of a trig sub problem, that didn't have any square roots. And what's more, if you rewrite this a little bit, you'll see that there is actually a square root hidden in here. This is the integral from 2 to 4 of 1 over the square root of x squared minus 1 cubed dx. Because the 3/2 power, that's precisely what the 3/2 power means. It means take the square root, that's the halves, and cube it, that's the 3. So this square root cubed is the same as the 3/2 power. Okay, so that means that the thing I'm looking at for my substitution is this, the x squared minus 1. So I need to think back to my trig sub Bible and ask, what should I substitute if I have something like this? If it was x squared plus 1, I would substitute for tangent. If it was 1 minus x squared, I would substitute for sine, thinking like 1 minus sine squared is cos squared. Since it's x squared minus 1, I'm going to substitute for secant, because secant squared minus 1 is tangent squared. So the move here is to let x equal secant theta. A here is 1, so you don't have to worry about that. Dx then is secant theta times tangent theta, d theta. And also, because this is a definite integral, I need to change my bounds. And some of this might be a little bit tricky. So first one, x is equal to 2. Then you'll have 2 equals secant theta, or secant theta equals 2, which means theta is the inverse secant of 2. Who can help me out with that? What is the inverse secant of 2? So for what angle between 0 and pi is the secant of that angle equal to positive 2? Might be helpful to remember that secant theta equal 2 is the same as saying cos theta equals 1/2. So instead of thinking of it as the inverse secant of 2, you could also think of it as the inverse cosine of 1/2. What's the inverse cos of 1/2? For what angle between 0 and pi is the cosine of that angle equal to positive 1/2? I warned you, you're going to have to know your inverse trig, right? Think about your unit circle. That's right here, pi over 3. Now on the exam, you're going to need to be able to summon these things, right? You're going to need to know these things. So if you need to spend some time refreshing your unit circle, reminding yourselves the definition of the inverse trig functions, all that good shit, take a look at the review resources material that I've posted to Canvas. There's several really good links there. The upper bound is harder. When x is equal to 4, we have secant theta equals 4, which would mean cos theta would be 1/4. This is not a nice number, so I'm just going to write it as the inverse secant of 4 and leave it like that. It's not an easy thing to sort out. So my new lower bound is pi over 3. My new upper bound is the inverse secant of 4. So my integral now runs from pi over 3 to the inverse secant of 4. Dx is secant theta, tangent theta, so I'll have secant theta, tangent theta upstairs, and then downstairs here, I'll have secant squared minus 1 under the square root, and then that whole apparatus cubed. Yeah, sorry for the bad handwriting, that's a 3. So is everybody comfy with what gets us to this step? the bound work here is a little bit wonky, like this is a weird upper bound. But everything else should be nice and straightforward. Any questions at all on what led us to this line? If not, then I'm going to go ahead and say, okay, secant squared minus 1, that's tangent squared. So I have secant theta tangent theta over the square root of tangent squared theta cubed d theta. The square root of tangent squared is tangent. Tangent cubed is tangent cubed. So this is this. And you can cancel one of the tangents from the numerator. You get secant theta over tan squared theta d theta. Which is not terrible. In fact, I swear I've seen this integral like 3 or 4 times in the last few days. I think at least one of our trig sub examples from Monday looked like this. My next step is going to be to rewrite this in terms of sines and cosines. So secant upstairs, that's a 1 over cos. That's 1 over cos theta times tan squared downstairs. That's the same as cos squared theta over sine squared theta upstairs. And we can cancel like this. I could shuffle. No, let's do it like that, yeah. So I'm left with cosine over sine squared. Yeah. All right, we did do this integral. We had another integral that came out to the same thing the other day. Does anybody remember how to handle this problem from here? There's 2 options. I think we looked at it both ways. You could substitute for sine, but I don't want to do another substitution if I can avoid it. So instead, I'm going to write this as cosecant times cotangent. This is the integral from pi over 3 to the inverse secant of 4, 1 over sine times cos over sine. Which is the integral from pi over 3 to the inverse secant of 4 cosecant theta times cotangent theta d theta. I know it's early, but I've had a distinct lack of feedback from you guys on this problem so far. So somebody help me out. Where can I go from here? What is the integral of cosecant cotangent? Please. My chat not showing up? Oh, that's it. Okay, I am getting feedback from you guys. I'm so sorry. My chat just wasn't showing notifications. Yeah, good. Negative cosecant. Negative cosecant. All right, the derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. So the integral of cosecant cotangent is negative cosecant. I'm sorry, I was giving you guys shit and it was all right there. So yeah, this is negative cosecant theta from pi over 3 to the inverse secant of 4. Now that upper bound, yeah, so the derivative of cotangent is negative cosecant squared. Nicholas and Griffin's back and forth there is fairly accurate. So we can evaluate this between these bounds to finish the problem. Plugging in the upper bound is going to be a little bit wonky. The cosecant of the inverse secant of 4 is not as nice as you would hope. That's going to reduce to an interesting little problem that you might have seen in trigonometry. What about the pi over 3? Can anybody help me with the cosecant of pi over 3? So I'm going to pop my negative out so I don't have to deal with it. And I'll have cosecant of the inverse secant of 4 minus the cosecant of pi over 3. So cosecant of pi over 3 is 1 over the sine of pi over 3. And the sine of pi over 3 is the square root of 3 over 2. So this will be 2 over the square root of 3. So this is negative cosecant of the secant inverse of 4 minus 2 over the square root of 3. Because the cosecant here is 1 over sine. 1 over sine at pi over 3 is 1 over square root of 3 over 2. And the reciprocal of square root of 3 over 2 is 2 over the square root of 3. What about this piece? Anybody remember from their trig classes seeing stuff like this? Oh, anybody remember how to handle stuff like cosecant of the inverse secant of whatever? Usually what we would do here is draw a little triangle. So it's a popular trigonometry problem to ask people to simplify this. I'm going to call this phi. So I'll let phi be the inverse secant of 4. You could use the letter theta if you wanted to here also. I'm just picking a different Greek letter so I don't confuse it with the variable theta I defined earlier. If phi is the inverse secant of 4, then the secant of phi is 4. In other words, the cosine of phi is 1/4. And I can use that information to draw a little triangle here. Cosine is the adjacent over the hypotenuse. And then I can use the Pythagorean theorem to complete the triangle. This squared plus this squared equals this squared. So this guy has to be the square root of this squared minus this squared. That's the square root of 16 minus 1, which is the square root of 15. Now remember what it is I'm looking for. I'm looking for the cosecant of phi. The cosecant of phi can now be read off from this triangle. Cosecant is hypotenuse over the opposite. So that's 4 over the square root of 15. So cosecant of phi is hypotenuse over opposite. It's 4 over the square root of 15. So altogether, my answer here is negative cosecant of phi minus 2 over the square root of 3. And you can distribute the negative if you want. That's 2 over root 3 minus 4 over root 15. So that's the game. This stuff, understandable if it's a little bit tricky. But really, it's very, very similar to what we would do if this was an indefinite integral, right? Drawing a little triangle like that and everything. So it should be coming back to you. Problems like this, like find the tangent of the inverse cosine of 7 or something like that, those sort of problems are problems that we should be getting, or should be familiar with, shouldn't be totally, totally foreign. Questions on this one? Okay, so you may want to, if you want to practice this skill, you might try finding the sine of the inverse tangent of 5, or the tangent of the inverse cosine of 1/3. Same sort of thing. You would let this be theta, so the tangent of theta is 5, and then you would draw a triangle, and then you would read off, you'd complete that triangle, and then read off from that triangle what the sine of theta is. The trick is to remember that inverse trig functions output angles. So you begin by calling this thing an angle. Begin by calling this thing an angle, just like I began by calling this thing an angle. And then you draw a triangle. So we begin by calling phi the inside there, the inverse secant of 4. That tells me that the secant of phi has to be 4. And then from that information, I was able to draw this triangle. From this triangle, I was able to read off the cosecant of phi. The cosecant of phi is the thing I wanted, cosecant of phi. So it's not too hard. And again, I recommend, if you're having a hard time with this, run through the same process for these two guys. If you get stuck on those would be great questions to bring by office hours. All right, I'm going to scroll up in the chat and see if there are any other problems there that you guys wanted to look at besides number 4. Looks like nobody else requested anything. Are there any other homework problems that you guys wanted to look at from the trig subsection so far? Give just a second for anybody who is still working on this. Mario would like to see number 8. Okay, we'll do that one next. And then there's time for one more, I think, before we switch into partial fractions. Oh, that coffee's terrible. Let's take a look at number 8. Nobody wants to see 7, huh? 7's a tricky one. I'm making an executive decision. We're gonna do number 7 after number 8, or at least something similar. Here we've got 3x times the square root of 1 minus x to the 4. This doesn't look exactly like one of our trig subtable things either. But x to the 4, remember, is x squared squared. So you've got several choices here. You could first make a little u sub. We could say, okay, well, I'm going to let z be x squared because this is the same as this. And I have here the x that I would need to make that substitution go through. So out would pop the 3, and I'd also have a 1/2. So I'd have 3/2 integral square root 1 minus z squared dz. That's one option. Another option is to jump straight in with the trigonometric substitution x squared equals sine theta. But I think for purposes of this class, it makes the most sense to do the z sub first. So then from here I would sub z equals sine theta. No bounds, but I do want to draw a triangle here. Since z is sine theta, I'm thinking of z as z over 1 and sine theta as the opposite over the hypotenuse. I would label my triangle like this, which would make this side the square root of 1 minus z squared. And then if I implement that substitution, dz, this is going to be cos theta d theta. This will be 1 minus sine squared theta under the square root. So I'll have 3/2 integral square root 1 minus sine squared theta times cos theta d theta. 1 minus sine squared is cos squared. And the square root of cos squared is cos. So this is cos theta times cos theta is cos squared theta d theta altogether. So this piece, the whole thing with the square root and all, that's cosine. Here's another cosine. So we'll have cos squared altogether, which is half angle stuff. So that would be, I'll pop out the 1/2, that'll be 3/4 integral 1 plus cos 2 theta d theta. Coming from the half angle identity, cos squared theta equals 1/2 times parentheses 1 plus cos 2 theta. I pop out the 1/2, turning this 3/2 into a 3/4. And then the 1 plus cos 2 theta is what it is. My antiderivative step. Looks like this. And before I even attempt to go back to my original variable, I'm going to apply an identity here. Remember that sine 2 theta is 2 sine theta cos theta. So this is 2 sine theta cos theta all over 2, and the 2's cancel. I do that because my triangle here has internal angle theta, not 2 theta. So I'd like to have regular thetas here, not 2 thetas. I can't read off the sine of 2 theta from this. All right. Because z is the sine of theta, theta is the inverse sine of z. And then sine theta, well, that's just z. Cos theta, that's the square root of 1 minus z squared. And now we're almost done. I have to go back through this substitution as well. So this is, I'll distribute the 3/4 at this step too. 3/4 times the inverse sine of x squared plus 3/4 x squared times the square root of 1 minus x squared squared is x to the 4. So that's the result in its full glory. Not too bad. Okay. Yeah, Nick. So drawing the triangle at this step, when I do trig sub, if the integral is a definite integral, I need to change my bounds, and the bound changing work would go here. If it's an indefinite integral without bounds, I know that I'm going to have to, at the end, at this step, I'm going to have to go back to my original variable. Drawing the triangle right at the start reminds me how to go back to my original variable in case I forget. So something I see from time to time is people getting to this step and then kind of panicking. And so rather than waiting until this stage to draw the triangle, I draw it right at the start, because that kind of reminds me that, oh yeah, at the end I'm going to have to go back to my original variable, and the trick for doing that is this triangle. So how did I know that sine theta was z and that cosine theta was the square root of 1 minus z squared? That all came from this triangle. Sine theta is the opposite over hypotenuse, that's z over 1. And cosine theta is the adjacent over the hypotenuse, that's the square root of 1 minus z squared over 1. So the step from here to here required this triangle. And I drew it at the start to remind myself that I needed to go back to my original variable. So it's just a habit that I'm in, and I encourage you to get into the same habit. Cool, okay. Any other questions on this one? Okay, then I have a question for you guys. Who remembers how to complete the square? because there's a family of problems here, kind of classic trig subproblems, which require completing the square. Number 7 is an example of such a problem. So this guy also does not look like something from our trig sub Bible. If it was x squared plus 6, that would fit the tangent substitution model. But it's x squared plus 6x. This piece isn't a constant. So what we actually need to do here is to complete the square underneath the radical. If you look in the modules, under my completing the square review, which is somewhere here. Yeah, here under trig sub 7.3. Take a look at this document. I put this together to help remind people how to complete the square. I recommend reading this. The proof of the quadratic formula, that's fun. If you've never seen that before, this is how you do it. But then the reason we do it is for stuff like this. So we need to complete the square under the radical. The way I do that, I take this number right here and I divide it by 2. Really, the first step is to make sure the coefficient of x squared is 1, but it is. So I'll take this number here, divide it by 2, and then square that. And then I add and subtract that number. So I take this, divide by 2, square it, then add that and subtract that. Certainly this is still equal to x squared plus 6x, because what I've done here is add 0. But now if I group it like this piece will always factor as a perfect square. This is x plus 3 squared minus 9. So that's how we get started here. Questions about the completing the square step there? Yeah, good, good, good. So Griffin's correct there. Are there any questions about how we're coming up with the x plus 3 squared minus 9? So then from here, I would want to sub x plus 3 equals 3 secant theta. This is like x squared minus 3 squared. Remember in your trig sub table, there's a reason I put u. I said u could be any linear function of x. Well, x plus 3 is a linear function of x. So I'm letting u, which is x plus 3, equal 3 secant theta. You could make a little substitution like u or z equals x plus 3, but it's silly to do that because du is equal to dz there. It doesn't, or dx is equal to dz there. It doesn't change anything. So you might as well do it like this. And then dx, the differential on the left-hand side is just 1 because the derivative of x plus 3 is just 1. And the differential on the right is 3 secant theta tangent theta d theta. I should also draw my triangle here. If x plus 3 is 3 secant theta, then secant theta is x plus 3 over 3. And I have to remember that secant theta is the hypotenuse over the adjacent. So this is x plus 3. This is 3. And this side right here is the square root of this squared minus this squared. That's the square root of x plus 3 squared minus 9. So there's my trig sub. And when I implement that substitution, I'll get the square root of 3 secant theta squared minus 9 times 3 secant theta tangent theta d theta. That's 9 secant squared theta minus 9 under the radical, and then 3 secant theta tangent theta d theta lingering. I can factor a 9 underneath the square root. Whoa, that's an ugly integral symbol, sorry. Getting us this. And now that's the square root of 9 tangent squared times 3 secant tangent. I can take the square root of 9 tan squared theta, that's 3 tan theta, times 3 secant theta tangent theta. So I've got a 3 times 3 that can come out front as a 9, and then I've got 2 tangents and 1 secant. So this is 9 times the integral of secant theta times tangent squared theta d theta. This is a tricky problem because the power of secant is odd and the power of tangent is even. This is kind of a nightmare. It's a looping integration by parts problem. Okay, so we would run IBP with U and dV. I'll choose dV to be secant tangent. And U to be tangent. I'm not going to run all the IBP here. It loops. And having done the loop, you will get 9/2 times secant theta tangent theta minus the natural log of secant theta plus tangent theta plus C. So this is a looping IBP problem. And we don't have time for me to run through this, but we've done this integral a few times. I've done this in office hours with people, and I've done this in class once or twice. So I trust that you guys can navigate from here to here. If you do get stuck on that, Go back and rewatch the videos from looping IBP. It was our second day on IBP, and we did this exact integral there. From here, though, we do need to go back through our substitutions. So while I have an answer, it's an answer in terms of theta, not an answer in terms of x. So secant theta, if you look at your triangle over here, secant theta is the adjacent over the hypotenuse. That's 3 over x plus 3. And tangent theta is the opposite over the adjacent. So I'll tell you what I'll do. I'll copy this down. My integral is equal to 9/2 times secant theta tangent theta minus the natural log of secant theta plus tangent theta plus c, which is 9/2. Now I can zoom in. Secant theta is the hypotenuse over the adjacent. So that's x plus 3 over 3. Tangent theta is the opposite over the adjacent. So that's the square root of x plus 3 squared minus 9 over 3 minus the natural log of those two things just added up. So x plus 3 over 3 plus the square root of x plus 3 squared minus 9 over 3 plus a constant. Certainly not an easy problem. If you get stumped on this, or if you want to see more along these lines, please check out that completing the square review that I posted to Canvas. It's under the module on trig sub. It's the only thing in the trig sub module right now. And I think that, that it will be helpful. We've got lots of algebra examples where I just show you how to do this step, how to complete the square. And then there's also an example where we do an integral using this stuff. So yeah, check that out. And if you want more practice on the looping IBP that we run into down here, go look at our second video from Integration by Parts. Okay. Questions on this? Any one step here that you guys would like to look at a little bit more? So I chose to make that substitution based on my trig sub Bible. So remember, if I have something like u squared minus a squared, then I want to substitute u equals a secant theta. So here u is x plus 3. I've got x plus 3 squared minus 3 squared. So I let u, which is x plus 3, equal a, which is 3 times secant theta. So that's coming straight from the trig sub Bible. It's a little bit complicated, right? It's certainly not as straightforward as if this was just an x and this was a 1. But it is the same rule that I'm following. That's a good question. Other questions on this one? Okay, then we do have a few minutes left in class, and in these few minutes, I want to sort of introduce what we're going to do in section 7.4. Ideally, I could say everybody remembers partial fraction decomposition from their pre-calculus class because we're supposed to cover partial fractions in pre-calc, but I know that that's probably not the case. And maybe not even due to any of your own fault. Maybe your pre-calculus class just never got there. Partial fractions is a process for taking rational functions. So we use, so it's called partial fraction decomposition. And you'll see me abbreviate it as PFD because partial fraction decomposition takes way too long to write. PFD is a process, purely algebra process, for splitting rational functions into sums of simpler rational functions. So you have to remember what a rational function is. It's a ratio of polynomials. It's a big fraction where the top and bottom are both polynomials, meaning sums of whole positive powers of x. If I had something like this, and I wanted to integrate it, for example, I know how to integrate 1 over x, and I know how to integrate 1 over x plus 2, but integrals don't play nice with multiplication. So I couldn't just integrate the 1 over x, integrate the 1 over x plus 2, and multiply them. That shit never works. If, however, I was able to split this up as something over x plus something over x plus 2, then I could do those two integrals separately because integrals do play nice with addition and subtraction. So the question is there a way to write this as something like this plus something like this? The answer comes from linear algebra, and the answer is always yes. If you think about it, when you add two things up like this, you have to have a common denominator, and that common denominator would be x times x plus 2. So something like this can come from sums like these. And with the appropriate choice of the constants a and b, you will get a true statement here. Overall, kind of the strategy in PFD, you have to ask, what sort of things could I add up to get something like this? And in this case, the answer is the only way you could get something like this as a sum of simpler rational functions is some constant over x plus some constant over x plus 2. In order to figure out the constants a and b, though, we have to do quite a bit of work. There's more than one way to skin this cat. I'm going to show you first how to do it kind of the long way, and then I will show you some shortcuts next week. If I wanted to, I could multiply both sides by x times x plus 2. So I'll have x times x plus 2 times 1 over x times x plus 2 equals a over x plus b over x plus 2 times x plus 2. On the left-hand side, I just get 1, because the x's and x plus 2's both cancel. On the right-hand side, I have to distribute. When I multiply a over x by x times x plus 2, the x's cancel, and I just get a times x plus 2. And when I hit this guy, the x plus 2's cancel, so I'll get here just b times x. If I distribute, I'll have 1 equals ax plus 2a plus bx. And then if I collect like terms, I'll have a plus b times x plus 2 times a. At this stage, I usually like to ask the question, if 3x squared plus 2x minus 1 equals ax squared plus bx plus c, can you tell me what a, b, and c have to be? Oh, Juan, you had a question there. Yeah, if the power of secant is odd and the power of tangent is even, those all require integration by parts. You won't see a lot of them, but like secant cubed or secant times tangent squared, your question from 902, those do all require IVP. Not all secant tangent integrals require that, but if the power of secant is odd and the power of tangent is even, then yes. Okay, so look at this, guys. If 3x squared plus 2x minus 1 is ax squared plus bx plus c, then a has to be 3, right? And b has to be 2, and c has to be negative 1. Yeah? So if I looked here, this is really 0x plus 1 equals a plus b x plus 2a. So the powers of x have to have matching coefficients. So a plus b has to be 0 and 2a has to be 1. You get a system of linear equations. Now, if 2a is 1, then a has to be 1/2. And if a plus b equals 0, then b has to be negative 1/2. That's the gain. All right, this is PFD. There's not a whole lot more to this, thankfully, unless you want to save time. But you have to remember what I call the PFD setup. So how could this possibly be expanded into simpler rational functions? This is the only way that makes sense. Depending on the different factors of the denominator, your setup will look different, right? If there was an x minus 1, then I would have plus c over x minus 1. But if this x was squared, or if this was an x squared plus 2, then things would be different. So this is where we're going to pick it up on Friday. I'm going to talk in more detail about how partial fractions work. I'll show you all of the cases for the PFD setup. This line I call the PFD setup, where you write your function equals some constants over some stuff. If I wanted to integrate this guy now, I could come back here and say a and b are both are 1/2 and negative 1/2 respectively. So this would be integral 1 over x times x plus 2 equals integral a was positive 1/2, b was negative 1/2, and then I would proceed with the integral like normal. This is 1/2 integral 1 over x dx minus 1/2 integral 1 over x plus 2 dx. This is a natural log. This requires a little z sub, but it's a straightforward one. So this would be 1/2 natural log absolute x minus 1/2 integral 1 over z dz. That'll also be a log. And then to finish things up, we would substitute back. So the good news is that the calculus steps in section 7.4 are going to be easy, right? Like this integral is not a hard integral. But first you have to do the PFD. You have to expand your function as a sum of simpler functions. The only other thing I want to caution you guys about or suggest that maybe you think about between now and Friday, vis-a-vis section 7.4, is polynomial long division. I strongly suspect that many people have forgotten how to divide polynomials, and that's okay. But if the rational function here had like an x squared upstairs, or an x cubed upstairs, or any polynomial of degree 2 or higher, then this would be called an improper rational function because the degree of the top would be larger than or equal to the degree of the bottom. If that's the case, then before you can even get started with this stuff, you need to divide the top by the bottom. So please do yourselves a favor. If you need practice with completing the square, check out this document. And then I would like everybody, regardless of whether they think they need practice with it or not, to take a look at the polynomial division stuff here. It's up to you. You can look at whatever YouTube videos you want, or you can look at like the Paul's Online page, Paul's Online Notes page about it. But remind yourself how to divide polynomials. And then on Friday, when we talk about this, I'm going to show you again all of the different ways that you can set up partial fractions. And then I'll also walk through some problems that require polynomial long division. And this section will go fairly quickly. It's not going to be hard because the calculus steps here are not hard. The only work is in the partial fractions itself. All right, so that's where I'm going to leave it for today. I hope you guys have a lovely rest of your day. Remember that the exam is being moved. So you get the multiples of the denominator multiplied by the original numerator and set them equal to find the numerator and solve. Griffin, that sounds about right. But we'll run through this in detail on Friday. So if you want to move ahead, of course, you can read the textbook. Yeah, PFD is hard to describe in a single sitting because there are several different cases and it's hard to write everything out in one way. But yeah, I'll leave it here. Remember, our exam has been moved from Friday of next week to Monday of the week after, which means we will be covering extra new material next week rather than spending a lot of time reviewing. So the impetus is on you guys to make sure you review and are ready for the test on the 5th of October. Zach, I recommend Cam Scanner if you're on Android. Yeah, CAMSCANNER. All right, yeah, any other questions, you guys? Feel free to shoot me a message on Canvas or come by my office hours. I'll have my normal office hour this afternoon. Okay, take care.